Hi guys, in this video we're going to take a look at pH versus pKa. Now these are two different things. They are related, but they're definitely different. So first off, we're going to talk about what pH is. So pH is a logarithmic function of the concentration of H+ in a solution. And you can define pH by a very simple equation. An equation you've probably seen before. pH equals the negative log of the H+ concentration. Now this is log log base 10, so this is a 10-fold difference when you're talking about pH units. This is log, not natural log, which is ln. Okay, so the scale for the pH scale is in general between 0 up to 14. Now I say in general, there are some very, very strong acids that actually have a negative pH, but for most cases, for things we're going to deal with in this class, we're talking about things that have a scale between 0 and 14. Okay, so if you're down towards 0 on the pH scale, this would be an acidic solution. Conversely, if you're up towards 14, this would be a basic solution, okay, if you were measuring the pH. And right here in the middle, okay, if you're at a value of 7, that would be a neutral solution. Pure water is actually neutral. It's actually pretty difficult to get to exactly 7 on the pH scale in terms of pure water. It's kind of hard to get actually really pure water. Okay, so that's the scale for pH. What I want to do in the next little section is actually show you some common solutions that you might be familiar with and kind of show you what those pH values actually are. So let's look at a couple common solutions that you probably have some familiarity with and look at what the pH of these actually is. So the first one we're going to look at is household ammonia. This is a common cleaning product. If you were to measure the pH of that solution, it's actually quite basic. That would be approximately 11. The next one, milk of magnesia, which you can buy over the counter. It's sort of, you often use it to calm your stomach. It's sort of an antacid. It actually is also fairly basic, has a pH of about 10.5. Blood has a pH that's actually fairly close to neutral, 7.4. So if you were to take a sample of blood, stick a pH probe into it, and actually measure the pH, it's typically right above the neutral value. Pure water, as we said before, on the pH scale is 7.0. It's actually pretty difficult to get pure water. If you were to measure the pH of tap water is not pure. It often has various ions and components in it. So if you were to measure the pH of just regular tap water, very rarely are you going to get a value of 7.0. Okay, now things that are somewhat more acidic, something like cherry juice, when you drink that, it has kind of a very bitter, kind of tart flavor to it. Cherry juice has a value of 3.6. If you were to drink wine, it also has a variety of organic acids in it, and this is fairly acidic as well, 3.0. And then lastly, something like stomach acid, you might expect with the word acid in its name, has a value of 1.7. So in our list here, things that are very high on the pH scale, up close to 14, these would be basic solutions. Conversely, as our pH value goes more towards 0, those would be acidic solutions. The last point I'd like to make about pH is coming back to the fact that when we define pH, this is a log base 10 function. So if we were to compare a solution that had a pH of 2 and compared it to a solution that was pH of 3, even though the difference in number on the pH scale is only a value of 1, the actual difference in the H+ concentration is a 10-fold difference in H+ concentration. So if I was at a pH of 2, that's a fairly acidic pH. If I were to go up 1 pH unit to pH 3, that would actually have 10 times less H+ ions, because we're becoming more basic, than the pH 2 solution. So when you're looking at this pH scale, just always keep in mind that this is actually a factor of 10. So if I were to go from, say, a pH of 4 up to a pH of 10. All right? So that's, okay, 6 on the pH scale, but that's actually 1 with 1, 2, 3, 4, 5, 6 zeros. That's a million-fold difference in the H+ concentration. Again, because this pH scale is a log base 10 scale. So in the next section, we're going to now contrast what exactly is the pKa. So in this section, let's take a look at what is pKa. pKa is an inherent property of a particular substance. So to think about this, I want us to consider the following sort of generic reaction. So if I had a reaction where an acid, which I'll just call that HA, is put into water, an equilibrium could be set up in the following way, where water is going to act as a base to pull off the proton of water, generating H3O plus A minus, which is our conjugate acid. So if we were to just have a generic acid reaction like this, this would be the way you'd write it out. So what pKa is really doing, it's giving us an indication of how strong this particular acid is at giving up its proton, or how willing it is to give up that proton. So if you look at this equation now, if the HA, the acid, is very willing to give up its proton, it would shift the equilibrium over more towards the products. Conversely, if HA was a very weak acid and didn't really want to give up its proton very much, that would actually shift the equilibrium back towards the left. So you may recall from your general chemistry that if we want to describe an equilibrium, we would use what's called an equilibrium constant, or KEQ, which is the concentration of the products divided by the concentration of the starting materials. When we're dealing with acids, we essentially do the same thing, but we'll describe this as the K sub A. It's essentially an equilibrium constant, but again, we're using it the A subscript because we're dealing with acids. So what is Ka then? Ka is going to be equal to the concentration of the products, H3O plus, times A minus, divided by the concentration of our acid. Now, one thing I do want to point out, you'll notice I didn't include water in this. It's implied on the product side there also is water here, and the concentration of water in a solution doesn't change very much, so essentially the waters would cancel out of this expression here. So in general, larger Kas equals more acidic. Okay, in other words, if the bigger this number is, the bigger the Ka value, it would shift the equilibrium to the right, and that would be because the concentration of H3O plus times A minus, the numerator of this fraction is larger than the denominator. Okay, so when you have large values of Ka, that's a more acidic solution. If you have small Kas, as you might expect, this is less acidic. All right, so that's the Ka. But what's now the relationship between pKa and Ka? So what is this relationship here? Well, like we saw before with pH, we're going to take the negative log of the Ka. All right, so pKa can be defined as the negative log of the Ka value. That's an important equation, definitely one you'll want to commit to memory. So we can talk about the Ka values, but in general, in organic and biochemistry, we more often than not convert these Ka values to pKas. And to do that, again, you take the negative log of your Ka value. So to take a look at the pKas of various compounds, I want to just show you some sample or some examples here, and then we're going to list out the pKa values. So if you were to put HCl into water and determine what the equilibrium constant, or Ka, was, and then take the negative log of that value, the pKa of HCl would then be -7. Okay, so that we know that HCl is a very strong acid, so here we have a value of -7. H3O plus hydronium ion has a value of -1.0. 7. Phosphoric acid, H3PO4, has a value of 2.2. And just to help you with this, I'm also going to just circle the proton that's being abstracted. So in the case of HCl, this is the proton that's coming off, and the pKa of that proton is -7. Likewise, one of the protons of H3O+ has a pKa value of -1.7, and so on. This next one here, this is acetic acid. This has a value of 4.5. Ammonium ion, if I were to pull off one of the protons of ammonium ion to give ammonia, its pKa has a value of 9.2. If I were to pull off one of the protons of water, it has a pKa value of 15.7. And then just to kind of compare this to some of the functional groups that we've talked about in our class, an alcohol, the OH proton of an alcohol, it's actually fairly close to what water is. Notice the similarity in water and an alcohol. These are usually about 16. They can range between 15, maybe up to 18, depending on the structure of the R group here. An alkyne, the terminal proton of a terminal alkyne is actually a little bit acidic, has a pKa of 25. And then lastly, something like an alkane or an alkene that just has a hydrocarbon, if I were to try and pull this proton off, its pKa value would be about 50. So let's now just look at this trend now. I've been going from negative numbers up to fairly large positive numbers. We know that HCl and hydronium, these are strong acids. Okay, so in general then, the smaller the number, or more towards 0 or even negative for the pKa value, that would indicate a strong acid. The acid is very, very willing to give up its proton. Conversely, if you have a very large positive pKa value, these are very weak acids. In other words, they don't want to give up their proton. Okay, so in terms of our trend, we would have increasing acid strength. Okay, so again, notice that each of these particular compounds has a different pKa. All right, that's different than measuring the pH, which was the concentration, or is related to the concentration of hydronium in a particular solution. So pKa is definitely different than pH, but it is related because we are actually measuring the amount of hydronium, H3O+, that's being given up. And so a scale like this is very useful when we're talking about various organic compounds to determine which protons may or may not be acidic or not. So the last point on pKa I'd like to make is really more of an example problem. One thing you'll often be asked to do is look at a chemical structure and determine which protons are the most or least acidic. So let's just take a look at this fairly simple compound. It has two functional groups. It has a carboxylic acid and an alcohol. In the previous section, I gave sort of the approximate pKa values of these. So if I were to look up in a table, and these are actually some pKas that you actually will kind of want to commit, not necessarily to memory, but have a general idea of which one's more acidic. So if I looked at a carboxylic acid proton, its pKa is between 4 and 5, depending on the structure. 4 to 5 for the pKa. An alcohol proton, those have values of approximately 16. Now, I listed those out in that little table in the previous section of the video. Again, you may want to go back and look at that table and sort of commit that, not necessarily to memory, but have a pretty good idea of where they are. Now, there are other protons that potentially could be acidic. Let's just look at one of these. This would be an alkane type proton. If I were to look at the pKa of that, that's going to be approximately 50 for its pKa. So again, if I were to try to look at this molecule and try and determine the most acidic hydrogen, we're going to look at and try and identify the proton that has the lowest pKa value. Remember, low pKa numbers mean that that proton is quite acidic. Conversely, very large pKa numbers means that a proton is not very acidic. So looking at this, the carboxylic acid proton would be the most acidic. Okay, it would be the first one to come off if you were to treat this with a solution of base, like sodium hydroxide. Conversely, this alkane proton, or any of the alkane protons on the ring, these are not acidic at all. So these would be the least acidic. Okay, and the alcohol proton will be somewhere in the middle. All right, so I hope that this video has helped explain the major differences between pH and pKa. You definitely want to get some practice problems in looking at these. Good luck.